Unit 4, Day 3, September 26th, if you're missed that day and trying to keep up at home. So Day 1 was exponent properties. It's kind of a brief review here. Exponents and their properties. Day 2 was exponent graphs. And now Day 3 is log properties and graphs. So kind of put them together today. F of x is 2 to the x. G of x is log base 2 of x, are inverses of each other. They undo each other. Well, we're going to get there. They are symmetric to each other with respect to the line y equals x. Because the easiest way to think about inverses is you switch x and y. And we'll use that a little later today when we go to graph them. And when you switch x and y, maybe it makes sense that you would end up with graphs that are symmetric across y equals x. Because how you got the other graph was by switching x and y. Another way to think of inverses is whatever g does, f undoes, and you're right back to x. Or whatever f does, g undoes, and you're right back to x. Got like a picture of that. This is just inverses in general. So x, whatever the input in, goes into f. F does something to it. G does something to it. But whatever g does, it undoes f, and so you're right back to x. That's what it means to be inverses. Like the simplest version would be f adds 3 and g subtracts 3, and then you're right back to where you started from. Logs and exponents are much more complicated, but it's that same idea. 2 to the x, and then log base 2 of x cancel each other out, and you're right back to whatever you started with. The point 0, 1 is on the graph of y equals f of x. Again, f of x is 2 to the x. So the point, if we're switching x and y, 1, 0, must be on the graph of g of x. The point 1, 2 is on the graph of f of x. So if we switch x and y, then 2, 1 is on the graph of g of x. Switching things around. The x-axis is a horizontal asymptote for the graph of y equals f of x. Maybe we should remind ourselves what f of x looks like. Let's see, that was 2 to the x. That looked like that. So if we switch x and y for inverses, then we used to have an axis or an asymptote on the x-axis, but if we switch things around, there's what g of x is going to look like. G of x is a vertical asymptote or g of x, has a vertical asymptote of the y-axis. If you switch x and y, all the x and y things get switched. I think once we get to actually graphing these, that'll sort of take care of itself. I wouldn't worry too much about that. Determining the values of logs. You guys have done logs before? Yes? Sadly. Did you do the fishhook thing or the loop-de-loop thing? Or okay, people call it different things. So the definition of log base 3 of 27 means 3 fishhook around 3 to some power is 27. So 3 to what power? What goes in the blank over here? 3. Okay, we don't really even think about logs, we think about exponents. We like mentally change it into an exponent and then come up with the answer. So log base 5 of 25, again, we're not really thinking logs. You're mentally envisioning the fish hook, maybe even physically drawing the fish hook. So what's the answer? What's the answer of log base 5 of 25? 2. Because the fish hook, 5 squared is 25. Now, hopefully you get to the point where you don't have to draw the fish hook every time, but you're still mentally doing it. 4 to what power would give me 1? 0. 10 to what power would give me 10,000? 1, 2, 3, 4. I can just count the zeros. 10 squared is 100, cubed is 1,000, fourth is 10,000. How did we end up with negative? I just gave away the answer.
It's a negative.
It's a negative. I meant to say, how did we end up with it flipped over? It's negative. So 2 to what power would give me 32? 5. So negative 5 would flip it over. Same thing with number 6. Got to be negative to flip it over. And 3 to the 4th would give me 81. So this is one of those things, is like, do you even really do logs? Not really. You kind of just change it into an exponent and think of it in terms of exponents. Now, in my mind, that's also what we can do to graph logs. Is like, I don't want to graph logs. I'd rather graph exponents. So let's do the same thing. Like, this is not how everybody graphs exponents. So, did y'all graph exponents last year? Do you know? Do you remember? Some yes, some no. Well, I think graphing them like I'm about to present them makes sense to me because it ties it together with all we know. The easiest thing to do with logs is the fish hook. And if we can just keep using that fish hook, then let's keep that idea in mind when it comes to graphing them. I'll show you what I mean. So y equals log base 2 of x. But again, I don't really know logs. I'd rather do exponents. So let's switch this thing into an exponent. So what would I get if I fish hooked that? It's on the other side, but it's still the same. 2 to the y equals x. Now, admittedly, that feels a little backwards from what we normally see. But I'd rather feel a little backwards with an exponent than deal with a log. So I'm still going to do my table of values. But here's where the backwards thing comes in. And by the way, we already said that logs and exponents are inverses, which means we switch the x and y, which is going to make sense of what we're about to do here. What values should I... Which values do I want to plug in? Do I want to pick x values or do I want to pick y values? Which would be easier to do?
X.
But we know x values.
We just could be easier to know than x.
Okay, which would be easier to evaluate?
Wait, what does the value tell us?
Well, okay, in some sense it doesn't matter, but usually I think it's going to be easier to plug in y values for this one. Because I can pick -1, 0, and 1, and it makes it look like what we did yesterday. I'm picking the exponent. Maybe that's a better way to say it. I'm picking the exponent just like I did yesterday. Yesterday the exponent was x. Today the exponent's y. But it's going to end up with the same, I shouldn't say points because they're backwards. It's going to end up with the same set of numbers. The x and y's will be switched though. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. Alright, so it's the same set of numbers we had yesterday, but x and y are switched. But that makes sense because logs and exponents are inverses of one another. So let's plot these. Again, this feels a little weird because we don't often pick our y's. We're usually picking our x's. But we did some switching around here. Alright, so 1/2 -1. 1, 0, 2, 1. And like yesterday, we could keep going and we could pick y to be 2, and that means x would be 4. And on the other end, you could get 1/4 and then 1/8 and then 1/16. But we get the idea. There's an asymptote there. So it's a log graph, but just like I didn't really evaluate any of these logs up here, I cheated and changed them into exponents. I'm going to do the same thing here. I don't want to learn a log graph. I want to use what I know. So I make it an exponent graph. All right, let's use our transformation rules rather than the fishhook. Like, I already know what the parent function looks like. Let's use parent function plus transformations, and that way I don't have to redo my table of values. So what's the +4 do to the graph? And the -3? Down 3. So kind of like yesterday, I could redo my table of values and subtract 4 from all the x's, and that would have some fractions in there, and then subtract 3 from all the y's. That'd be a lot of work. It'd just be a lot easier if I just moved the whole axis, or the whole origin, left 4, and down 3, and make that my new starting point. My new origin, and then from that new origin, use that set of points that we already came up with. So 1/2, -1, 1, 0, 2, 1, 4, 2 if you want to. Label or call attention to the asymptote here. What's the asymptote equal to? Or what is the equation of the asymptote? Oh, I hesitate to draw it in with my blue marker because then that covers up the new origin, but you get the idea. Number 3, what's the negative out front going to do? Be careful when you say flip it, I agree, but are we flipping it left and right or up and down? Up and down. So which set of coordinates, the x values or the y values, which one am I multiplying by negative? Which one is affected here? If I want to accomplish an up and down flip, that would be the y values. So my origin is still 0, 0. I didn't move anywhere, but I'm going to change my y values. So you kind of have options here. If you can handle it visually, like so, if I flip that upside down, it would look something like that, and then I can kind of go point by point. If that feels a little strange, then we could multiply the y's by -1. That's easy to keep up with. Again, if you can visually do it, go for it. If you're a little hesitant to figure out, like, hey, we just learned how to graph log, now we're going to like just in our brain flip it over, like, multiply the y's by -1, and then we'll get our new points. 1/2, 1, 1, 0, 2, -1, 4, -2, I feel better about showing my points on that one. And that one has an asymptote. I guess the asymptote flipped over as well, but it stayed x equals 0. Number 4, what's that negative going to do? It's going to flip it, but which way is it flipping it? Left and right. It's a left and right flip, which means it affects the x values. So kind of the same thing. If you want to do it without multiplying, that's fine. If you want to multiply the x values by -1 and come up with them, that's fine. How about we try it without writing down the points this time? 1/2 -1, so I'll go -1/2 -1. And -1 0. -2 1. -4 2. So if you need to, you can write them out if that helps you sort of slow down and make sure you get the points right. If you can flip it kind of on the fly, that's okay too. And the asymptote is still x equals 0, or the y-axis, either way. But let's not forget where we started with this thing. Graphing logs, we pulled a trick, because we don't like logs, we prefer exponents. So we do the same trick we always do with logs. Use the little fish hook thing, and then you don't have a log anymore. Now you've got your standard points. You can move them around however you need to after that. All right, some information that you don't really need, but maybe it's interesting, so we'll kind of go through this quick. Again, we don't often put questions on tests, history questions, but the common log is log base 10. Right? Again, you don't usually write log base 10. If it's not there, it means base 10. This is used in science, pH scale, so that's chemistry stuff, Richter scale, earthquake, decibels, all use base 10 logs. Have y'all seen any of this stuff in physics or chemistry? Chemistry, pH scale, definitely, right? Yeah. Most of you are in physics right now. Sound is second semester, so you'll get there with decibels, where you get to use logs again. I know that's exciting. In this course, if a log is not written with a base, it's assumed to be base 10. It's sort of like square root is assumed to have a 2 as the root. There's other, like if I just had x, what's the power on that? 1. What's the coefficient on that?
1.
So there's other places where we don't write a number and you know that there's a number there. And so log is one of those spots where if we just write log base x, or log of x, it's base 10. We don't have to write the 10. Just like we don't have to write the power of 1, we don't have to write square root. There's just hidden numbers. I guess if the number's common enough, we just all assume that whichever one it is. Natural log is a log with base e. So log base e, but we don't ever write log base e. It's so common that we switch it to just ln. This also has lots of science uses and definitely calculus uses. You can't do geometry without pi, and you can't do calculus without e. Remember, e is 2.718 blah blah blah. In calculus, we'll get to a formal definition of where that comes from. So why ln versus nl, right? Natural log would be nl. Well, not everybody speaks English, right? Newsflash to you. And the theories both come from the idea that this wasn't an English-speaking thing to start with. So in Latin, logarithmus naturalis, maybe I'm saying that right. So that would be ln. Another theory is that the guy that came up with this stuff, I don't know how to say his name. His last name is Euler. Euler, like the Houston Oilers, not Euler, but Euler. So it's possible that he called it, again, I'm not going to attempt the French, but you guys that are in languages, a lot of times the adjective comes after the noun, right? Spanish, French, apparently. maybe in Latin. And so he would have used this, and it would have been ln. Who knows? So log natural, that's how I say it, and that's my French pronunciation of it. I don't know what that is. Either way, ln, natural log, nl, but again, it's ln. And e, right, when you come up with stuff, you get to name stuff after you. So Euler, his name started with E, so we get to use the E for his name. Right? So when you come up with something famous, you get to name it the Patel method. And you get to use P as some famous letter. Right, I use the word with both of you, so you can both think you got credit for something. Terminology. The expression log base b of a is pronounced log base b of a, or log of a base b. Either way, kind of the same thing. B is the base of the log. The reason is, if you do the fishhook thing, right, you'd have b to something equals a. That's the base. The base must be positive and can't be 1. The reason it can't be 1, so you'd have 1 to something equals, but what's 1 to anything? 1. And so if you had a base of 1, like, you wouldn't really get anywhere. That doesn't even make sense. So it's got to be positive, and it can't be 1. A is the argument of the log. That's what you're taking the log of, and it must be positive. Again, think about the fishhook thing. If you have b to something equals a, and we've already said b is positive, then if I raise a positive number to anything else, I'm always going to get a positive number. Right? Because what would a negative exponent do? That's what throws people off. But what does a negative exponent do? Flips it over. It's still positive, it's just flipped over. What would a fractional exponent do? Like 1/2. That would be, power over root. That would be a root kind of thing. But it wouldn't make it negative. So the argument has to be positive. So A is positive and B is positive. All right, we looked at properties of exponents. Because exponents and logs kind of go together, their properties kind of go together. So x to the n plus m, this is small, right? Here we go. We can break up a log like that. So if the argument is multiplied, you can split them up and add them together. I assume y'all saw this last year if you did logs last year, because this is one of the earliest things you would do with logs, is use these properties. These properties are huge in calculus. They took a test today that wasn't specifically about this, but their life got a whole lot easier if they remembered this property. Haven't graded them yet. I hope they did this because it made the problem a lot easier.
Did you practice AB or BC?
This year, AB.
What about next year?
Who knows? Probably Miss Murray. She's been doing BC for a while. But she's awesome, so you'll be fine. If multiplication leads to addition, what do you suspect division leads to?
Subtraction.
Oh, look at you guys go. Log base b of n minus log base b of m. Now, some of these properties, if you just think about the fishhook, you can figure them out. They're not really memorized things. B to what would be 1? 0. Okay, so that equals 0 because b to the 0 equals 1. Again, so this is not memorize a bunch of stuff. This is think about the fishhook and figure everything out from there. B to what power would give me b? 1. Right? I don't know that you would get this one from the fishhook thing, but power to a power, we multiply, and so what we can do is take this power and move it down front. So if the argument has a power on it, the power can come down front. I'm kind of starring the ones that I think are most useful. Certainly in calculus, those three we use to make our lives easier. You do a little bit of algebra on the front end and it makes your calculus life easier. Change of base formula. Hold on, let's back up to this. Because we get confused, log base b of n. If all of that is to the fourth, well, that 4 can't go in front, right? Because something to the fourth is not the same thing as multiplying by 4. But if the 4 is on the end, like what we're taking the log of, then it can come down front. So that's what gets people in trouble. They try to put that 4 down front. No, you can't. If you got something raised to the fourth, you can't just move the 4 in front. But the log property is, if you're taking the log of something to the fourth, you can move the 4 to the front. Change of base formula. Occasionally this is helpful if b is like a base you don't want to mess with. If you're going to a calculator, really this comes from the land before calculators. That's a long story. I wasn't even alive then. But they had log tables. Maybe your parents may have heard of them. They probably weren't even alive for them either. Like if you didn't have a calculator and you wanted to know the log of 12, like there would be printed books, like the back of the PreCal book would have log tables in it, and you could look up the log of 12. Well, if it's base something else, they're not going to make log tables with every single base. That'd take up way too much space. So there's a way to change the base from b to 10, or from b to e, natural log a over natural log b. So any base you like, you can change the base. And sometimes that's helpful to make the rest of the computation easy. A little side note here. Log base 2 of x plus 3 means log base 2 of x plus 3. Like if there's not a parentheses around the argument, then that 3 is not part of the argument. If you want to include it in the argument, you got to have it in parentheses. Now, this is not really good notation. Like I don't like that because it tempts you to think that it's the same as this, but it's not. Right? It would be much clearer if this person had written this as 3 plus log base 2 of x. So it's not wrong, it's just not clear. So be careful. If you want to take the log of it, you better put it in parentheses. Okay, let's actually work some problems here. I think these are going to go faster than all the notes put together here. Log of 1/5. Well, I don't know what the log of 1/5 is, but I look at my answer choices and I start to think, okay, I see that I need to use some property here. How did you get C?
It's flipped.
Yeah, I'll show the step that you're not even showing or saying. 1/5 is 5 to the negative 1, and then the negative 1 can come out front. And so, yes, it's negative log of 5. A different way to do that would be to use that first property and make it log of 1 minus log of 5. And log of 1, so 10 to the what would give me 1? Oh, 10 to the 0 would give me 1. And then 0 minus log of 5 would be negative log 5. So you could get on that one. You could get there two different ways. Speaking of division and subtraction, let's see. So that could be log of 12/48, which is the same as log of 1/4, which I don't have as an option, but now this is sort of like number 1, right? I could rewrite that as log of 4 to the negative 1, and then move the negative out front. Or I could do this, split it up and do log of 1 minus log of 4. Either way. Oh, number 3. Okay, this combines some things. Basically, if things are added, if logs are added, that means you can multiply their arguments. If they're subtracted, you divide their arguments. So anything with a negative sign is going to go to the bottom. Right? That sort of makes sense because a negative exponent would flip things over. A positive exponent would be in the top. So 16's in the bottom. 1's in the bottom, but that's not really going to do anything. And then 8's in the top. And then hopefully that all reduces to something nice. Let's see, how do we want to do this? It doesn't really matter. 32 over 4 is 8. 8 over 16 is a 2 in the bottom. So natural log of 4. Of course, that's not an answer choice. Which one of those things is the same thing as the natural log of 4? D, because you could rewrite that as 2 squared, or you could look at your answer choice and realize, well, I could put the 2 back up as the power, and 2 squared is 4. Number 4 is kind of the same as number 3, but we're going in reverse. So anything in the top is going to be added. So natural log of 2 plus natural log of the cube root of x minus 7. Anything in the bottom is subtracted. Minus natural log of 10 minus natural log of x plus 9 to the 6th. Not one of my answer choices. Oh, I see natural log 5. That suggests that maybe I should have reduced the 2 and the 10 first. So that would be a natural log 5 in the bottom, or excuse me, 5 in the bottom, so negative natural log 5. Now that's on all of them, so that didn't help anything. I could move the 6 out to the front, so I should have a minus 6 natural log x plus 9. Minus 6 natural log x plus 9. So I'm down to B or C. What about this cube root thing? What's that? Cube root, what power is the same thing as a cube root? 1/3. And then we take that 1/3 and move it down front. Down front of the log, not just into the denominator, so that's C's out. So it is B. Okay, just trying to sandwich all our properties into one problem there. And then 5 is sort of the backwards problem. Here it is all spread out. Let's write it as a single log with one argument. Okay, dare we try to do this all in one step? Yes. Okay, so what can I do with this 3? Make it x cubed. And then this 4 can go up as an exponent, but that's subtracted, so I need x plus 5 to the 4th in the denominator. 1/5. I could write it as 1/5. That's fine. They probably want you to recognize that that's a fifth root. And then 8 to the top. Well, 8 to the exponent, but minus sends it to the bottom of the argument. And so that's a mess, but that's what they're looking for. Sandwiching it all into one argument. So we want you to get adept and good at spreading them out, sandwiching them up together. Spreading them out, sandwiching them up together. Because depending on the problem, sometimes it's nice if it's all spread out. Sometimes it's nice if it's all scrunched up. Evaluate. X equals 8, W equals 3. Alright, so just plug in things. 8 minus 5 is 3. 8 plus 1 is 9. Minus 3, natural log. 3 minus 7 is negative 4. But I got the absolute value bars on here to fix that. To fix the negatives. 3 plus 1 is 4. So 3 natural log of 1/3 minus 3 natural log of 1. Let's do the easier one first. Like I see a bunch of 3's in my answer. I don't see any natural log 1's. Why is that? Zero. Because the natural log of 1 is 0. So that part's gone. I don't have 3 natural log 1/3 anywhere, but that's because I could rewrite that as 3 to the negative 1, and then put the negative out front, and then it's answer D. Again, lots of property work today. So properties and graphing as well. So worksheet 3, the assignment. But I want to show you worksheet 3. Let's get started on it a little bit together. It's been a few minutes. Number 1, I don't know what the graph of log base 5 of x is. So what should I do? I would rewrite it as 5 to the y equals x. And then I can pick some y values. And after that, how will you graph 2, 3, and 4? Based off of graph 1. And use the things you know about left 7, down 3. Some kind of flip, the other kind of flip. But you'll have the key points. So graph 1 might take longer than the others because you got to come up with the parent function. And then you can write, or then you can do the other things with it. Same thing with number 5, although what's the base here? E, so e to the y equals x. And so that same thing where I can pick my y values, come up with some x values, and so take your time on number 5. Get number 5 clean and accurate and looking good, and then you can use number 5 to graph the rest of them, because after that you're just using your transformation properties. So again, 6, 7, 8, 2, 3, 4. I mean, yes, you're graphing logs, but you're not really graphing logs. You're just taking a graph you already know and moving it around. And then after that, it's more property work.